Hi guys. So today I'm going to be talking about dot products, which is the next topic. So lately we've been doing vectors. Now we're going to switch to dot products. And basically what dot products are is you have two vectors. So you have two vectors here, and you're basically getting their product. So how do we do that? Well, here, if we're given some product, or I mean some vector A with these components, and another vector B, then the dot product of that would be A times B. And what's happening here is we're multiplying the first components, the second components, and the third components, and we're adding them up basically, right? So yeah, that's what we're doing. We're adding them up here, right? Hang on. Yeah, so we're adding them up, and it's going to be a real number basically. So the dot product is, sometimes it's called the scalar product or inner product. And yeah, for 2D, it's pretty much the same as 3D. So here in this example one, we're multiplying two vectors here. So we're multiplying their components. So 2 times 3 plus, and then their second components. 4 times -1, we get 6 minus 4, we get 2. And it's the same idea for in 3D, right? So we have -1 times 6 plus 7 times 2 plus 4 times -1/2, and we get 6. And it's also the same for ijk. So here we just translate them into normal vectors like this. And we do the same thing. 1 times 0, 1 times 0 plus 2 times 2 plus -3 times -1, and we get 7, a real number 7. And here we have some properties. So if A, B, C are vectors this is in 3D, and C is a scalar, then we have these properties. So if we multiply A times A, we get its magnitude squared. A times B is the same as B times A. But yeah, we have these different properties that definitely make sense. And we actually proved two of them, if I remembered correctly. So we did A times A, and we said that A is a vector of components A1, A2, A3. And remember when we multiplied, we're multiplying A1 times A1 plus A2 times A2 plus A3 times A3. So we basically just square them. And when we square them, it's basically their magnitude to the power of 2, right? Then we also did for the third property, A times B plus C. We translated them into vectors. And then here you notice we added it, vector sum. And then here we multiplied it. We multiplied A1, A2, and A3 to each of these, right? So we have A1, A2, A3. We multiply them to B1 plus C1, B2 plus C2, B3 plus C3. And then we eventually got to a new vector. Well, not really a new vector, but we got to the conclusion that A times B plus A times C. This thing is basically this thing, which we showed here above. So that's that. And then we also gave a geometric representation in terms of theta. And the idea here is basically if theta is the angle between two vectors A and B, those two vectors, then we have this formula where if we get the dot product of A and B, it's just the magnitude of A times the magnitude of B cosine theta, which is basically law of cosines. And we actually, yeah. So here we're basically going to prove it. So how do we prove it? Well, we have the magnitude AB squared, right? AB squared. So this one, we square that, and that's basically equal to OA plus OB squared, right? And then we actually continue this proof where we do 2 of the length OA times the length OB cosine theta, because that's the law of cosines, right? We have c squared, a squared plus b squared minus 2 ab cosine of c. And this is true if, let's say, we have a, b, c, a, b, c, and we want to find, say, the angle of c, which is theta, right? But we're given what a and b are. And we're also given what c is. So that's that. So basically, this law of sines, law of cosines, they're used to find sides and angles of, to be honest, any triangle, as long as it's a triangle. So yeah, this case, same idea, but we just used vectors, right? And then here we observe that the law of cosines still applies in the limiting cases where theta is 0 or pi, or a is 0 or b is 0, right? And let's say, but let's say this magnitude OA is A, right? OB, just to make it look cleaner, is B. And AB is A minus B. Then this will basically become A minus B squared is equal to A squared plus B, whoops, B squared minus 2 A B cosine theta, right? Which is very, very similar to our law of cosines. And using these, we can actually use some properties of the dot product and rewrite the left side, right? So here we use properties 1, 2, and 3 to rewrite the left side. So what are properties 1, 2, and 3? Well, basically it's this one. These guys here. Right? So how do we do it? Well, so it's A minus B. And this is the same as A minus B times A minus B. right? So we just expanded it a bit. And then this is the same as A times A minus A times B minus B times A plus B times B. So again, we did more expanding here in this case. So we did FOIL method, A times A, and then minus, or A times negative B, so minus A times B, and then we have the inner, so minus B times A, and then minus B times minus B, which is just positive in this case. So we just expanded it a bit more. And then this is basically using property 1, right? And then it's the same thing here, right? And then this is 2AB, right? Because we say that this thing is the same as this thing, so we just add them together and we get minus 2. Let me just add this. So now I have this so far. So this looks a bit familiar though in algebra, right? And then this is now equal to that previous thing that we got here, which is this, plus minus 2AB cosine theta. And so what does this mean? Well, this means that this thing is basically the same as this thing. And we can just get rid of the negative 2. Right? So that's the idea there. If we multiply A times B, it's the same as the magnitude of A times magnitude of B times cosine theta. Right? Okay, let's go through an example here. We already did an example 1, so we're doing example 2. And here the question is, if the vectors A and B have lengths 4 and 6, and the angle between them so what's the angle between them? Well, it's pi over third. Let's find A times B, right? So we can actually use something that we solved earlier. So we can actually use this. So we basically just use a formula that we had. Right? So we use this thing. Since you want to find A times B. We're given that the length of A is 4 and the length of B is 6. And the angle between them is pi third. So you can just plug this stuff in. So we have 4, 6, cosine of pi third should be A times B. So what is this? 24 cosine pi third. Hopefully my calculator gets a number. I gets 1/2. So this is 24 divided by 2, so this is 12. Right? So that formula, it actually also enables us to find the angle between two vectors, right? I'm gonna Google this because it says in the textbook corollary. I don't know what that means. Probably something in math, maybe. Oh, so in mathematics, a corollary is a theorem that follows directly from another theorem with a relatively short and straightforward proof. So it's like a sub-theorem. So the corollary, or like a sub-theorem, based on the original one that we got, is that if theta is the angle between two, I'm kidding, between non-zero vectors A and B, then we have cosine theta, which is A times B, over the magnitude of A times magnitude of B. And this makes sense, right? Because we just divided this thing by this. Uh-oh. And in a way, this cancels out. So we have that. That's how we got that formula there. Okay. Let's solve an example. So the example here says we want to find the angle between, so we're given vectors with numeric components. So vectors A, which has 2, 2, 1. Is it 2, 2, 1? Oh no, 2, 2, negative 1. And B, which has 5, negative 3, 2. And yeah, so we want to make use of this formula that we got, right? So how do we do that? Well, we already have A times B. we want to find their lengths, right? So here we want to find their lengths. So how do we do that? We just use distance formula. So we have this 2 squared, 2 squared, 1 squared, 4 plus 4 plus 1, so 9, 3. Then for B, same idea. 5 squared, negative 3 squared, 2 squared. And we have 25 plus 9 plus 4. So it gives us square root of 38, which I am not bothered to simplify. And then let's actually also find A times B. So A times B is just multiplying these and adding them together, right? So we're doing this times components of B. And as we're multiplying each component, we're adding them. So 2 times 5 plus 2 times negative 3 plus negative 1 times 2. We get 10 minus 6 minus 2. So that's 2. Right? And so we just use that formula that or that corollary. So that is cosine this is 2. This is 3 square root 38. And so the angle between is just our cosine of this thing. Which is approximately 1.46 radians or 84 degrees. Right? Okay. Here we have two non-zero vectors A and B are called perpendicular or orthogonal, same thing, if the angle between them is pi over 2. Right, so we're saying here, if we have two non-zero vectors, I'm assuming they're A and B, are perpendicular. So these two vectors are perpendicular or orthogonal. If angle between them is pi half, right? Or 90. And so that theorem is A times B is equal to this, right? Here, this would result to 0. Their product, right? Yeah, because they're perpendicular. So that's why it equates to 0. Mm, and conversely, if a times b is 0, then cosine theta is 0. So theta is equal to pi over 2. Yeah, but basically their dot product is 0 if they're perpendicular. Reason is basically cosine pi over 2 is 0. So if this is 0, you multiply it to all of them, then everything becomes 0. So yeah, that's the idea. If their dot product is 0, then that means vectors A and B are perpendicular. I can't give an intuitive definition, maybe? Can't think of one. Yeah, it would be interesting to see, though. Yeah, and then fun fact, if we remember the 0 vector, that is considered to be perpendicular to all vectors. And so here we have the following method for determining whether two vectors are perpendicular slash orthogonal. So the idea is basically two vectors, namely A and B, are orthogonal or perpendicular if and only if their dot product is 0. Right? And let's see that in an example. So here we have to show that this vector here, 2i plus 2j minus k, this vector is perpendicular to 5i minus 4j plus 2k. And the way to show this is we just get their dot product, we equate it to 0, right? So how do we do that? Well, we just multiply them basically. So the way to do that is this. Oopsies. We multiply their components. Right? And we get 2 times 5 plus 2 times negative 4 right? Yeah. Plus negative 1 times 2. This is 10 minus 8 minus 2, which is basically 0. So indeed, this vector here is perpendicular to this vector. Yeah, because their dot product is 0. Okay, now I actually have some interesting facts here, which I'm going to go over. Okay, let's go over this. So, oops, wrong color. So because, let's say, our cosine theta is greater than 0, if let's say our angle is in between 0 and pi half, right? Cosine is obviously greater. And we also say that cosine theta is less than 0 if, well, our pi half is less than theta, which is less than or equal to pi. So here we see that a times b, or the dot product of vectors a and b, is positive for theta that's less than pi over 2. And it's negative for theta greater than pi over 2. Right? So we basically think of a uh, a times b in terms of measuring its extent to which a and b point in the same direction. And so the dot product is positive if a and b point in the same general direction. Yeah. So I'm not gonna, actually, no, let's scrap this. So the idea basically is how we can use dot products to determine angles, right? So let's say we have this A, and they're generally going positive, right? This A and B, we have this theta here, then their dot product is positive, right? And if it's positive, their theta, or their angle, is acute. Acute meaning it's less than 90, right? And then here we say that, oh, A is going this way, B is going that way. This is a right triangle. If it's right, then basically what we mentioned earlier is that the dot product is 0 because these two vectors are perpendicular or orthogonal to each other. So that means our theta is pi half, or 90 degrees. Right? And lastly, well, if this is going, A is going the other way around, this is our angle, this is A, this is B, then that means their dot product is less than 0, it's negative. And so that means their theta is obtuse, or it's greater than 90. So that's how we can tell the angle, given that we have two vectors that are kind of adjacent to each other. We can use the dot product to determine what's our angle. Like, what is it? We can get a general sense of it, or we can pinpoint exactly what the angle is in radians or in degrees. Right? But let's say we also have extreme cases, right? So let's say A and B are pointing at the exact same direction, then obviously, if they point at the exact same direction there, then our theta is 0, right? So cosine theta is 1. And basically, their dot product, if let's say cosine theta is 1, is basically their lengths. So A times their dot product is equal to a multiplication of both their lengths. And another extreme case would be they're in completely opposite directions. And here we basically have a 180 or a pi, right? So let's say this was A, this was B, and they're pointing exactly the opposite directions. Then, well, we have the case where cosine theta is -1. And if cosine theta is -1, then their dot product is negative of the multiplication of their lengths. But those are extreme cases, right? So that's that. Yeah. I'm gonna be honest, I still find it like difficult to get the idea of how dot products. Yeah. They're really hard to use to determine angles, but there is some relationship to them. I mean, based on what we can tell. And I think it's just mainly based on law of cosines that we're able to do it. Right? But yeah, I think it's also just the proving that made it possible. Okay. Let's see how long this is. Okay, how many more examples? Oh, okay. I think we can do more. We can do some examples here. I'm gonna try my best to explain it. Um, yeah, I mean that's what the purpose of me doing videos for is. I go through a new concept, and if I can't explain it, well, that's my problem. But I'm gonna try my best. And doing videos for me, at least like this, helps me explain and understand the material better. So yeah, and hopefully, I mean, at least you guys get something out of it too. Okay, now we're doing direction angles and direction cosines. And so the direction angles of a non-zero vector A are angles alpha, beta, and I don't know what that y is. um, what is y in Greek? I don't know how you say it. Upsilon. Yeah, I just realized they use Greek letters for angles, which is funny. Theta is a Greek letter, kind of looks like an O. Okay, so basically what this is saying is uh, the direction angles of a non-zero vector A, what are their direction angles? Well, they are angles alpha, beta, and epsilon. I don't know if I wrote that right, but you guys get the point. It looks like a Y. Uh, in this interval between 0 to pi. Right, because 0 is an extreme case, pi is also an extreme case. So those are our intervals. That makes, so the direction angles of a non-zero vector A are angles alpha, beta, epsilon. So they're three angles in some interval that makes oh, oops, that A mixed with positive axes, X, Y, and Z axes. So we're referring to the foreground, right? And we actually have a picture to go with it. Ooh, lucky picture. At least I don't have to draw this. So here's I'll copy paste the picture. So here's the picture to go along with it. So we can see this is the foreground, right? That's the foreground. And we have A, the vector, and we have angles here. So, this is interesting. So we have our first angle in terms of x. So it goes from here to here. That's our alpha. And then from y, that's our beta. And then for epsilon, for our z part, is that one. Don't know why they made it y. Maybe they don't have like a Greek letter for z. Or it's used in something else. I don't know. But yeah, so the idea is there. And what we're saying is that the cosines of these angles, of these direction angles. Oh, so these are direction angles. Yeah. Direction angles. Namely cosine alpha, cosine beta, and cosine epsilon. So they're called what we call direction cosines. Nice name, very original. So they're called direction cosines of vector A. So like vector A is pointing here. Wow, very, very red. And we have these like angles accompanying it, or these direction angles. Because we have a vector which has direction, right? So we also have angles to go along with it. But this time it's in 3D, so we have 3 angles to look out for. Okay, so let's look at some terms here. So remember that corollary that we had. We have B, we replace it with I. What do we get out of that? Well, we have cosine alpha, which is A times I, right? Because we replaced it. And A times I is A1, right? How do I know? I is a standard basis vector, right? This is 1, 0, 0 from the last chapter. And A, if we multiply it by this, is going to be left with, let's say A is some value here. I don't even know what A is. Oh, A is this vector, right? A has some value, A1, A2, A3. And if we multiply it to I, so if we multiply this to I, well, we're only left with A1. Because we do A1 times 1 plus A2 times 0 plus A3 times 0. Anything you multiply 0 is 0. So it's going to be A1 plus 0, which is just A1, right? Then we have their magnitude here, which is just A. Because the magnitude of I, this thing, if we use the distance formula of that, it's just 1. And we multiply 1 to this magnitude, then it's just the magnitude itself. Because anything you multiply by 1 is just itself, right? 5 times 1, 5, 4 times 4, 4. So yeah, we have that. And we're putting numbers here, apparently. So I'm going to put numbers. Okay, and then similarly, We also have, I don't know, what do we have? We have a 9. Amazing. Oh, so that was for our alpha right here. That whole thing was our alpha. So we're just using that corollary that we had earlier. Okay, very interesting. And now we're going to data, right? And here we're looking at the y component. So A2. Oh, basically same idea. And our epsilon is A3. Right? And so if we square these expressions, right? Let me check. Yeah, we square these expressions. We actually have something like this. Cosine squared alpha, cosine squared beta, cosine squared epsilon. This is 1, right? Yeah. Still thinking why it's 1 though. We have A1, A2. Interesting. A3. And we're also dividing it by its magnitude. So that's surprisingly weird, but interesting. Yeah, we're just can't really tell from right now. So I guess I just have to move on and see. Um, but yeah, I can't tell right now why it's 1, but we'll see about it. And for equations 8 and 9, okay, that's interesting. Why is that actually? Yeah, so we have, let's see. We have this A2, A3. And let's say we square each of them, right? Um, don't know. And then if I factor out maybe this thing, see where the math will take us. A squared 1, A squared 2, A squared 3. Right? This, oh, I see it now. So this is 1 alpha squared. This whole thing is that distance squared. Yeah. And so we can cancel that, we get 1. That's why. I'm gonna include that. Yeah, because we have this cosine and we have this. So yeah, we're going to include that. That's how it became 1. Actually, let's do this. Yeah, a full proof. Dang. Math is so fascinating because you just don't know how how everything works. Then you just try a bunch of things and you're gonna be like, oh, wow, it works. But yeah. And then we can also use equations 8 and 9. It says here, and we can write something like this. Oh no, this isn't right again. Okay, so we have our vector A here with the 3 components. And we can actually write something like this. Funny enough, that length cosine alpha uh, length cosine beta, length cosine epsilon. How? It's because of this thing. Or was it this one, right? So we just multiply it. So from here, A1 is their length times cosine of the Greek symbol. And same goes for beta and epsilon, or for the other two components. And so that's how we were able to come up with these things. Okay, now what? Oh, scaling, right? So we can factor out this alpha. Oh, I'm not kidding. I'm kidding. I mean this length. And now we get this thing. Scaling, right? And then, oh, there's another way of proving it, funny enough. If we remember our unit vector, right, we can divide this. We get A over its length, which is this thing. And we know this is 1. That's a unit vector. It's always going to be 1. Right? So that's fun. Yeah, that is fascinating. So that says that the direction cosines of A are the components of the unit vector in the direction of A. What a tongue twister. Anyway, but yeah, that's what this thing is explaining. Okay, now we move on to another example here. And here the example is, we want to find the direction angles. Of a given vector, so you have vector A. Surprising. And we have components 1, 2, 3. And so how do we do that? Well, we just make use of our formulas, right? Okay. So which formula here can we make use of based off of what we have? Well, if we're given each of these, then we might as well so the idea here basically is to find the direction angles. So we want to find cosine alpha, or direction cosines, right? Cosine beta, cosine epsilon. So how do we do that? Well, we have a formula here that can actually help us find it. And it's this thing. These guys here. That's what we can use, right? We already know A1, A2, A3. That's 1, 2, 3. Now we just need the length. And then once we divide them, then that's it, right? So, Well, how do we do that? We just get their length. And we just use the distance formula. So 1 squared plus 2 squared plus 3 squared. And here we have 1 plus 4 plus 9. And that is 14. Did I get that right? 1 plus 4 plus 9. Yeah, it's 14. So square root of 14. Then we want to use our pieces to put things together. So we have a1, which is 1 over square root of 14. We have our cosine beta, which is a2. This is 2 over square root of 14. And our cosine epsilon, which is a3. This is 3 over square root of 14. So that's our direction angles right here. Right? Actually, not yet. Now we want to find, yeah, I just realized the direction angles are alpha, beta, and so now we want to find alpha, beta, epsilon. We want to find those three angles. How do we do that? Well, we basically get their arc cosines. So alpha is just the arc cosine of 1 over square root of 14, which is approximately 74 degrees. If I did not mess up the math. Oops. Or I mean my calculator. Yeah, it's about 74 degrees or 74.5, 74. We'll just do that. And then our beta here is the arc cosine of 2, which is approximately 58. And last but not least, our epsilon is the arc cosine of 3 over square root of 14, which is 37. Right? Yeah, so those are those three angles. Okay, now let's yeah, I think we'll probably end it there. It's getting pretty late. But yeah, I hope you guys learned something. I'm still learning this. But yeah, I mean, this is some interesting stuff. Like, you use the dot product, you're given a vector, and you're using that dot product to find the direction angles, right? But it's still pretty abstract to me. I don't know, like, what's the purpose of it and all, but I'll definitely see that. And I'll definitely show you guys when I find something interesting. So yeah, that's pretty much it for now, and I'll see you guys in the next one.